Welcome to the Platform Engineering Playbook podcast, where everything you hear is built, reviewed, and improved by AI, by me, and by you, the listener. This show keeps me, and hopefully you, up to speed on the latest in platform engineering, SRE, DevOps, and production engineering. It's a living experiment in how AI can help us track, explain, and discuss the fast-moving world of infrastructure. Every episode is open source. If you've got something to add, correct, or challenge, head to platform-engineering-playbook.com. You'll find all the content and a link to the GitHub repo. Open a pull request, join the conversation, and make the playbook smarter. Let's get into it.
Welcome to Episode 7 of Kubernetes Production Mastery. Last episode, we mastered networking, services, ingress controllers, CNI plugins. You can route traffic anywhere. Your architecture is beautiful. But here's the question nobody asks until it's too late. Is it actually working? Your ingress is routing 10,000 requests per minute. Great. How many are errors? What's the latency? When did the error rate spike from 0.1% to 5%? You have no idea. You're flying blind. Pod-to-pod networking across your service mesh looks healthy, but what's normal latency? 50 milliseconds? 500? When should you be concerned? Database connections maxed out at 3 a.m. last Tuesday. Which service caused it? When did it start? Without observability, these aren't questions you can answer. They're mysteries you debug for hours. Today, we're fixing that. By the end, you'll understand the 3 pillars of observability: metrics, logs, and traces. You'll deploy production-ready Prometheus with persistent storage and service discovery. You'll design actionable alerts using the 4 golden signals that prevent 90% of production surprises. And you'll know exactly when to use metrics versus logs versus traces for debugging. Think of production observability like an airplane cockpit. You don't fly with a single engine temperature gauge. That's monitoring, sure, but it's inadequate. You need comprehensive instrumentation: altitude, airspeed, fuel level, heading, engine temperature, hydraulic pressure. Why? Because failures are multidimensional. Your CPU might be fine, but memory's leaking. Network looks healthy, but disk is full. Application responding, but requests timing out. This is why we have 3 pillars of observability. Each answers different questions. Metrics are your vital signs: numbers over time, request rate, error percentage, CPU usage, memory consumption. Metrics answer what's happening right now and what's the trend. They're perfect for detection. Your dashboard shows error rate jumped from 0 to 5%. Now you know there's a problem. Logs are your security camera footage, event records, error messages, stack traces, audit trails, application behavior. Logs answer, what exactly happened at 3:42 a.m.? They're perfect for diagnosis. Metrics told you errors spiked. Logs show you connection timeout to backend API service. Now you know which service. Traces are GPS package tracking for requests. One user request touches 5 microservices. Trace shows you the complete path and timing for each hop. Traces answer, where did this slow request spend its time? They're perfect for distributed diagnosis. Logs showed backend API timing out. Traces show backend API spent 29 seconds waiting for the database. Now you know the root cause. Here's the decision framework. When you're debugging, ask yourself, is there a problem? Use metrics for detection. What exactly went wrong? Use logs for diagnosis. Which service in a multi-service chain caused it? Use traces for distributed diagnosis. You need all 3. Without all 3, you're debugging with missing puzzle pieces. Let me make this concrete. It's 3:42 a.m. You're monitoring alerts, 502 errors spiking. You check metrics. Error rate went from 0.1% to 5% in 2 minutes. That's detection. You're awake. Now what? You check logs. Filter by timestamp. Filter by status code 502. Logs show connection timeout to backend API. That's diagnosis. You know which service. But backend API is healthy. CPU fine, memory fine. Where's the bottleneck? You pull up traces. One trace shows front-end to API gateway, 50 milliseconds. API gateway to backend API, 100 milliseconds. Backend API to database, 28,000 milliseconds. There's your problem. Database query taking 28 seconds. Now you can fix it. Remember Episode 4's troubleshooting workflow? Observability gives you the data to actually execute that workflow. Describe, logs, events, those commands now return useful information because you've instrumented your cluster properly. Now let's talk about Prometheus. Here's the mistake I see constantly. Someone runs helm install Prometheus, works great in development, deploy to production. 2 weeks later, Prometheus pod restarts. All metrics gone. Why? No persistent storage. Or Prometheus crashes with out-of-memory errors. Why? No retention policy. Metrics filled the disk. Or metrics exposed to the entire cluster with no authentication. Or you manually configure every scrape target and miss half your services. Default Prometheus installations fail in production. Here's what's missing. First, persistent storage. Remember episode 5? Prometheus needs the same treatment as databases. StatefulSet with a persistent volume claim, 500 gigabytes to 1 terabyte. Retention configured for 15 to 30 days. When the pod restarts, metrics survive. Second, service discovery. You shouldn't manually list scrape targets. That's unmaintainable. Use service monitors, custom resources that tell Prometheus what to scrape. Deploy a new service with the right labels. Prometheus automatically discovers it and starts collecting metrics. No manual intervention. Third, security and resource limits. Prometheus shouldn't be accessible to every pod, and it needs memory limits. Otherwise, high cardinality labels cause out-of-memory kills. Here's the production architecture. Prometheus server runs as a stateful set with a PVC, retention policy set to 30 days. Alert Manager handles alert routing, grouping, and silencing. Grafana provides visualization, querying Prometheus with PromQL, and service monitors provide automatic target discovery. For deployment, I recommend Prometheus Operator over plain Helm charts. Why? Operator gives you custom resources for declarative configuration. Service monitors, Prometheus rules, Alert Manager config, all Kubernetes resources. Helm charts work, but you'll manually create service monitors and manage config maps. Operator is more Kubernetes native. Let me show you a real example. E-commerce platform. What does Prometheus scrape? Cube state metrics for cluster state, pod status, deployment health, node conditions. Node exporter for host metrics, CPU, memory, disk I/O on every node. Your ingress controller for HTTP metrics, request rates, latencies, status codes. And your application pods for custom business metrics, like cart abandonment rate or checkout completion time. Now here's what matters most, the 4 golden signals. This framework comes from Google's SRE book. These 4 metrics cover 90% of production issues. Everything else is noise. The signals are latency, traffic, errors, and saturation. Latency is how long requests take, not just average. You need percentiles, P50, P95, P99. Why percentiles? Average latency might be 100 milliseconds, but P99 is 5 seconds. That means 1% of users wait 5 seconds. Unacceptable. You need to know. Traffic is requests per second or bandwidth. Are you handling 10 requests per second or 10,000? This tells you load and helps identify capacity issues. Errors are request failure rates, 400s, 500s, timeouts. Your error rate should be below 1%. Above that, users notice. Saturation is how full your system is. CPU usage, memory usage, disk usage, database connection pool utilization. Saturation at 90% means you're close to capacity. Time to scale or optimize. These 4 signals apply to every service. Monitor them, alert on them, and you'll catch problems before customers complain. Let me show you the PromQL queries. For latency, you use histogram_quantile function. This calculates the 95th percentile from Prometheus histogram metrics. For traffic, you use rate of total requests over 5 minutes. For errors, you calculate error rate as 500s divided by total requests. For saturation, you compare current usage to limits, memory usage divided by memory limit. Remember episode 6's networking? These queries monitor your ingress endpoints, your services, pod-to-pod latency. The infrastructure you built last episode now has visibility. Here's where people mess up Prometheus. High cardinality labels. Cardinality is the number of unique combinations of label values. Low cardinality example, you have 10 services and 3 environments. That's 30 combinations. Totally fine. High cardinality example, you add user ID as a label. Now you have millions of combinations because every user gets a separate time series. Prometheus runs out of memory. Best practice for labels, use them for dimensions with low cardinality. Service name, environment, instance, job. These have limited unique values and high diagnostic value. Don't use labels for identifiers with high cardinality. User ID, request ID, email address, session ID. If a label has more than 100 unique values, reconsider it. If it has more than 10,000, it's definitely wrong. The rule, labels are for aggregation dimensions, not identifiers. You want to aggregate by service or environment. You don't aggregate by user ID. That's a filter in logs, not a metric label. One more thing on Prometheus, storage costs. Production pattern is short-term metrics in Prometheus and long-term metrics in Thanos or Cortex. 15 to 30 days at full resolution in Prometheus. 1 year or more in Thanos with downsampling. Why? 1 terabyte of retention times 3 replicas equals 3 terabytes of storage. That gets expensive. Thanos uses object storage, like S3, much cheaper for long-term retention. Now let's talk logging. Without log aggregation, you're in trouble. 50 services times 5 pods each equals 250 log sources. Pod restarts mean logs disappear. Debugging requires SSH to 20 different pods, grep through logs, and pray you find the error before it rotates out. Centralized log aggregation fixes this. All logs flow to a single queryable system. Logs persist beyond pod lifetimes. You can correlate logs across services using request IDs. Filter by timestamp, service, error level, all in one interface. The choice is Loki versus Elk Stack. Here's my decision framework. Autoknow is Grafana's log aggregation system. It's lightweight and low cost because it only indexes labels, not log content. It integrates perfectly with Prometheus and Grafana. Same query interface, same dashboards. And it's great for Kubernetes because you can tail logs just like kubectl logs. The downside is limited full-text search. You can't do complex Elasticsearch-style queries. Loki is best for teams already using Prometheus and Grafana and for cost-conscious organizations. You'll save on infrastructure because Loki doesn't need massive Elasticsearch clusters. ELK Stack is Elasticsearch, Logstash, and Kibana. The benefits are powerful full-text search, complex queries, and advanced analytics with custom dashboards. The downsides are resource-heavy. Elasticsearch needs 4 gigabytes of memory minimum per node, and higher cost because it indexes everything, not just labels. ELK is best for large teams with dedicated log analysis staff, compliance requirements for detailed log retention, or when you need advanced search capabilities. My recommendation? Start with Loki. It's simpler and cheaper. Migrate to Elk later if you hit limits on search capability or need compliance features. Most teams never need Elk's complexity. One critical practice: structured logging. Unstructured logs look like this: 2025-01-12-1432-10. Error. User login failed for John at example.com from IP 203.0.113.5. You can read it, but querying is painful. How do you find all login failures from a specific IP range? You write complex regex and hope it works. Structured logs are JSON. Same information, but queryable. You have timestamp, level, error, event, login failed, user, John at example.com, IP address as separate fields. Now you query with Loki. Show me all events where event equals login failed and IP matches this range. Simple, fast, accurate. Best practice, applications log JSON, FluentBit parses and forwards to Loki or Elasticsearch, Grafana or Kibana for querying. The cost trap with logging is retention. Logging everything at debug level generates 10 terabytes per month. 7-day retention is manageable. 90-day retention costs a fortune. Production pattern. Info level for general logs. Error and warn always logged. Debug only during active troubleshooting. 7-day retention for general logs, 30 to 90 days for audit logs if compliance requires it, and archive to S3 or Google Cloud Storage for long-term retention. Object storage is cheap, and you can search it if needed. Now alerting. This is where most teams fail. Bad alerting looks like this. Alert on every single error. You get 100 alerts per day. Alert fatigue sets in. You ignore them. Alert on symptoms without context. Disk usage, 70%. So what? Is it growing? Will it fill? No grouping. 20 pods crash? You get 20 separate alerts instead of one. Good alerting focuses on customer impact. Alert when error rate exceeds 1% or latency P95 exceeds 500 milliseconds. Alert on imminent failure. Disk at 90% and will fill in 2 hours based on growth rate. Group-related alerts. All pods in a deployment down equals 1 alert, not 20. Let me show you real alert rules. High latency alert. P95 latency exceeds 500 milliseconds for 5 minutes. High error rate alert. 500 errors divided by total requests exceeds 1% for 5 minutes. High memory alert. Pod using more than 90% of memory limit for 10 minutes. Notice the pattern? Alerts trigger on rate of change plus duration threshold. This avoids alerting on transient spikes. A single slow request doesn't page you. 5 minutes of slow requests does. Alert Manager handles smart routing. Critical alerts, error rate above 5%, go to pager duty and wake up on call. Warning alerts, disk 80%, go to Slack for business hours review. Info alerts, deployment completed, just log them. Grouping is key. 20 pods crash, 1 alert. Deployment X unhealthy, not 20 separate alerts. And silencing for planned maintenance. Deploying a fix, silence alerts for 2 hours so you're not paged during the rollout. Remember episode 4's troubleshooting workflow? Alerts tell you what failed. Metrics and logs tell you why. This is the complete picture. One more pillar, distributed tracing. Here's when you need it. User reports checkout is slow. That request touches 6 services: front-end, API gateway, cart service, inventory service, payment service, order service. Metrics show all services healthy. CPU fine, memory fine, error rate low. Which service is slow? This is where tracing saves you. Your application code generates spans, timing information for each service call. A collector aggregates spans from all services. Storage, like Jaeger or Tempo, stores the trace data. The UI visualizes the complete request flow. Example trace shows checkout request took 2.3 seconds total. API gateway took 50 milliseconds, cart service 100 milliseconds, inventory 80 milliseconds, payment service 1900 milliseconds, order service 170 milliseconds. There's your problem. The payment service is slow. Now you check the payment service's metrics and logs for the root cause. You need tracing if you have 10 or more microservices, complex request flows you can't easily follow, or latency issues you can't diagnose with metrics alone. You don't need tracing for monoliths or fewer than 5 services, simple architectures where you can follow request paths easily, or when metrics and logs are sufficient. Sampling strategy matters. Don't trace every request. The cost and performance overhead aren't worth it. Sample 1% of successful requests for trend visibility. Sample 100% of errors for debugging. This gives you enough data without killing performance. Call back to episode 6. If you implemented a service mesh like Istio, tracing is already enabled. Istio automatically generates spans for every request through the mesh. Let me walk through common mistakes. Mistake 1. No Prometheus retention policy. Metrics fill the disk, Prometheus crashes, you lose all data. Fix: set retention to 30 days and storage size in your StatefulSet PVC. The flags are storage.tsdb.retention.time equals 30D and storage.tsdb.retention.size equals 450 GB. Mistake 2. High cardinality labels. Prometheus runs out of memory, queries are slow, scraping fails. Example, adding a user ID as a label creates millions of time series. Fix: use labels for dimensions like service and environment, not identifiers like user or request. Mistake 3. Logging everything at debug level. Log storage costs explode to 10 terabytes per month, and queries are slow. Fix: info level in production, error and warn always, debug only during troubleshooting. Mistake 4. No alerting or too many alerts. You either miss critical issues or ignore all alerts because of fatigue. Fix: alert on customer impact using the golden signals, group-related alerts, and route by severity. Mistake 5. tracing at 100% sampling, performance overhead, storage costs, and no benefit over 1% sampling for trends. Fix, 1% sampling for successful requests, 100% for errors. Let's pause for active recall. Answer these questions. First, what are the 4 golden signals and why do they matter? Second, you're debugging a slow checkout flow in a microservice architecture. Which observability pillar would you use first and why? Third, your Prometheus is running out of memory. What are the 2 most likely causes? Here are the answers. The 4 golden signals are latency, traffic, errors, and saturation. They matter because they cover 90% of production issues. If these 4 look healthy, your system is probably fine. Everything else is noise. For debugging a slow checkout in microservices, start with traces. Traces show you which service in the chain is slow. Then check that service's metrics for latency and errors. Then check logs for specific error messages. Traces give you the where, metrics give you how bad, and logs give you the why. For Prometheus out of memory, 2 causes: high cardinality labels creating too many unique time series, or no retention policy, storing too much data. Check your label design and set retention limits. Let's recap. 3 pillars of observability: metrics for trends, logs for details, and traces for request flows. You need all 3. Prometheus production setup requires a StatefulSet with a PVC, a retention policy, service monitors for automatic discovery, and avoiding high cardinality labels. The 4 golden signals are latency, traffic, errors, and saturation. Alert on these, not everything else. For logging, choose Loki for cost and simplicity, or Elk for power and compliance. For tracing, implement it only for complex microservices with 10 or more services. Sample smartly, 1% success, 100% errors. This connects to previous episodes. Episode 4's troubleshooting workflow now has data sources, metrics, logs, and traces. Episode 5's stateful sets apply to Prometheus storage. It needs PVCs and stable identity, just like databases. Episode 6 is networking. Services and ingress are your monitoring targets. Service monitors discover them automatically. You can now build production infrastructure, secure it, persist state, route traffic, and see what's happening in production. Next episode, we tackle cost optimization. You've built production-ready systems, but what's it costing? The 5 sources of Kubernetes cost waste, right-sizing strategies using FinOps principles, tools like KubeCost, and the senior engineer problem, over-engineering costs money. We'll use today's Prometheus metrics to monitor resource utilization and Episode 2's resource concepts to right-size workloads. See you then.
That's it for this episode of the Platform Engineering Playbook podcast. Every topic, transcript, and summary you just heard lives out in the open at platform-engineering-playbook.com, where anyone can suggest updates or add insights through GitHub. If you've got thoughts, fixes, or new ideas, open a PR. And if you enjoyed the episode, rate us on your favorite podcast platform. We're always shooting for 5 stars. While you're there, give the project a star on GitHub. It helps others find and contribute to the Platform Engineering Playbook. This podcast is generated by AI, reviewed by AI, me and you, a community of engineers keeping our craft sharp. Thanks for listening, and see you next time inside the Platform Engineering Playbook.